Okay, so at the beginning, this is just going to be a quick introduction to what is linear algebra, so you know what this course is about, or at least give you a quick overview of what linear algebra is. So, an introduction to linear algebra. For today, this is probably mostly just me talking without doing any calculations yet. Not till I actually get to problems in the book will I be doing. So, an introduction to linear algebra. So first off, what is linear algebra? So linear algebra is the study of linear transformation between two finite dimensional vector spaces. No, nice and fine, but linear algebra was something I didn't understand. Linear transformation is something I don't know. And finite dimensional is something I don't know. And vector space is something I don't know. So let me at least explain that. So I've given you something you don't know in terms of more things you don't know. But let me explain what I'm sort of talking about. So first, before I tell you what a vector space is, let me give you sort of a historical context for it. And then I'll say, well, this is a vector space. And then I'll say, no, this really isn't a vector space. So let me give you some intuition. So first, a geometric vector. And so a geometric vector, let's say vector V here, is this arrow. So it's this thing where it starts, it has some initial point, and it has some terminal point. So you start somewhere and you end somewhere else. So people like to say, well, a vector has a length and a direction. Okay, so what can I do with vectors? Well, I can add two vectors by just taking one vector and then taking the other vector and moving it so that the initial point for this other vector starts at the terminal point for the other vector. Then, if I start at the initial point for this u and at the terminal point for v, then this new vector is u plus v. If I have some vector u, I can stretch it or I can compress it. And so I can draw another vector in the same direction, but just having a different length. By, let's say, if this was 2, I could double the length, or if it was maybe A here was 3, I could triple the length. Or maybe if A is a half, it's -1, well, it'll be the same vector, but in the opposite direction. So I can somehow get another vector in the same direction or opposite direction if it's negative as the original vector, and just having a length that is now a time, or absolute value of a times the original length of the vector. So what can I do with vectors? Well, I can add two vectors, and I can multiply a vector times a number, a scalar. So I will call a number that I'm multiplying a vector by a scalar. So what is a vector space? Well, a vector space is what you can do with vectors. And so if u is a vector and v is a vector, then u plus v is a vector. Vectors are closed. A vector space is closed under vector addition. Suppose I have some number, s, for scalar, and I have some vector u. Then my vector space is closed under scalar multiplication. If s is a number, u is a vector, then s times u is also a vector. And so we saw that sure, it's a vector because it's just a vector in the same or opposite direction, but possibly with a differing length than the original vector. Next, vector addition is commutative. So u plus v is the same as v plus u. Next, vector addition is associative. U plus v plus w is the same as u plus v plus w. Next, there's a zero vector. It's a vector that has no length and no direction. And so there exists some zero vector such that u plus 0 is just the vector u. There exists a vector negative u such that u plus negative u is the 0 vector. It is the vector in the opposite direction. If you take this vector plus its opposite, well, then you get, you go here, then come back, so you get back to where you started from. So you've gone nowhere. The number 1 times the vector v is just the vector v. If you multiply by 1, you're not doing anything to the vector v. If you take the number a and you multiply that by the sum of the vectors u and v, then this is the same as a times u plus a times v. Scalar multiplication distributes over vector addition. And similarly, a plus b times u is the same as a times u plus b times u. So now, you notice I put little arrows here to say that these are vectors and all that. Very shortly, when we're doing linear algebra, we don't put little arrows over things because they're going to be so any object that satisfies these 9 conditions is said to be a vector space. And any sort of scalar that, well, is from a field is a possible number that we can use for this. So what is a vector space? Well, this is a vector space. A vector space is some algebraic entity that satisfies these 9 conditions, okay? If it satisfies these conditions, then we say it's a vector space. Any member of a vector space is called a vector. So even though it may not look like what you think of as a vector, it doesn't have a length, a direction, whatever, we call it a vector because it's a member of a vector space. So let me do an example. So this is a vector, but it's probably not what you think of as a vector. And so let C with the superscript 0 of the closed interval AB be the set of all continuous functions on the closed set AB. Then I will define vector addition. And so f plus g at x is just f of x plus g of x. Next, c times f evaluated at x is just c times f of x. If we give this as vector addition and this as scalar multiplication, then c superscript 0 on the closed interval AB, this is going to be a vector space. And so this is, and you're like, well, but wait, it doesn't look like an arrow. And the answer is, yeah, that's right. No, and so these vector spaces I'm talking about aren't little arrows. They are members of this thing. So, and you're like, wait, you know, what's going on here? So in mathematics, what we do is we abstract a concept. Why do you extract a concept? So we have this idea of a vector. Well, vectors are very useful. And so if we abstract it, maybe we can use these techniques that we use for vectors in other contexts. So that's one reason to abstract in mathematics. One, you may be able to use the tools that you obtained in another area in a different area. And so you allow the tools to be used more universally. Next, another important reason to abstract is maybe if once you abstract it, you'll only look at the most important aspects of the particular object. This will simplify the concepts and make studying those particular things that you were originally looking at much simpler than what they would be if you only looked at the specific example that you were looking at. And so abstraction, one, helps you to solve new, innovative problems. Two, it makes them easier. And so that's why we abstract. So in this case, my vector space is a set of functions. So note, a member of a vector space is called the vector. In general, we do not denote vectors in this class with little arrows because this guy doesn't look like an arrow, so we're not going to put a little arrow above it. A subspace. Let U be a subset of V. This is called a subspace of the vector space V if U is a vector space under the same vector addition and scalar multiplication as the vector space V. And so suppose I have a whole bunch of vectors here and I take a subgroup, a subset of them. Are they still going to be a vectors? A vector, are they still going to be vectors? Yeah, vectors and multiplying vectors. It turns out that U, a subset of the vector space V, is a subspace if the zero vector is in U and U is closed under vector addition and scalar multiplication. So those are the only properties we need to check to see if something is a subspace. A linear combination. So suppose you have some vector. Can you write it as, and suppose you have, this little vector here and this little vector here. Can you write it as a scalar multiple of this plus a scalar multiple of the other guy? Well, I don't know, can I? That is called a linear combination. And so a linear combination of the vectors v1, v2, vn is the following. Sum the scalar a1 times the vector v1 plus the scalar a2 times the vector v2 plus ... the scalar an times the vector vn. This is called a linear combination of the vectors v1 through vn. So a set v1 through vn is said to be a basis for the vector space V if every vector in V can be written as unique linear combination of these vectors. They should be on, they should be, yes, they should be there. Let me just check. Do vector space has, yes, it has to be all nine. It must satisfy all nine. If it does nine, it is not a vector space. So it must satisfy all nine of them. Let me just check at this moment. Yeah, you can download them. Okay, good. So the answer is yes. They should all be available, I think, for the whole semester. They're all there. Now, these are actually lecture notes that you can look at before a class or whatever. Usually what happens is I take those lecture notes or whatever so that I do new calculations actually during class. So this stuff here, which is sort of the, the definitions and all that, that I keep, because you don't want to, it's boring to see me slowly write definitions down. It's easier just to read definitions and better for you. But for calculations, I actually do all calculations, in front of you. It's students like to see calculations done rather than read. So all the lecture notes should be there. Usually what will happen is I will re-download the newest lecture notes that I had from class, replacing the old ones. But they're going to look virtually the same, with minor details maybe changed. Next, in here, so how many vectors there are in a basis is called the dimension of your vector space. So if every vector in your vector space can be written as a unique linear combination, so it was only one, there's only one linear combination of these vectors, then we say that these vectors are a basis for your vector space. Okay. As I say, after today, I'm not going to put arrows on anything. But for right now, I'm putting arrows because this is a little bit of an intuitive idea of what's going on. Every finite dimensional vector space has a basis. Okay, so I've told you this is a really quick introduction. Oh, this is a really quick introduction to, wait, let's minimize this if I can. A really quick introduction to vector spaces. Now let me talk about linear transformations. Okay, so let T be a function from V to W. Oh, what is a transformation? A fancy name for fun. Why do we call it transformation? I don't know. Because we want people to be impressed by this fancy term. So, like operators, we study operators. Well, what are those functions? So, a transformation is usually a function in a particular context, such as a linear. When you say it's a linear transformation, that a linear transformation is from vector space to vector space. By the way, sometimes they call these linear maps. Okay, but I will always call them linear transformations. I don't know, because I want to sound impressive. I don't know. But I'll call them linear transformations. So let T go map the vector space V into the vector space W. So let V and W be vector spaces, such that the following. T of U plus V is TU plus TV. Oh, now, usually a function evaluated X is done as F with a parentheses. For transformations, even though they are functions, uh, usually don't put the parentheses. So we usually don't write it as this, but write it as TU. So why? I don't know why. It's historical. So what is a linear transformation? Well, it maps from vector space to vector space, and it does these linear things. T of U plus V is TU plus TV. T of AU is ATU. Sometimes people write this as one property. Maybe I'll do it in red. T of AU plus BV is ATU plus, and now why did I put parentheses there? Don't know. ATU plus BTV. Okay, so you can combine both of these properties just into this one property. Maybe I'll say it. If and only if. So these are equivalent. Sometimes I'll do linear transformations this way. Sometimes I'll do it split up into those two. It depends on my mood. So what's an example of a linear transformation? What's a linear transformation? Well, it's taking one vector and sort of transforming it to another vector. So maybe you take a vector and you rotate it, or you squash it, or you compress it, or do combinations of those. So somehow, getting some vector and making it into this vector is a linear transformation. So you've gone from one vector to another, doing some particular thing. Okay. Okay, so let D, good, go from C1 to C0, where C1 is the set of continuously once differentiable functions, and C0 is the set of, well, zero differentiable, meaning just continuous functions on R. So then D is a linear transformation. Then D is a linear transformation where I define D as, I didn't tell you what D is. D is a derivative. Then D being the derivative is the linear transformation. I'm gonna have to rewrite this because it didn't tell you what it is. So what is D of F plus G? Well, it's just F plus G prime. Take the derivative. Well, what's F plus G prime? Well, I know that F plus G prime by the sum rule is just F prime plus G prime. Oh, the sum rule is this first linearity property, the fact that it's a linear transformation. So it's df plus dg. Next, daf, let's see if that's equal to the following. Well, that's that's af prime by the constant multiple rule, we get this is A times F prime. Oh, this is the constant multiple rule. This constant multiple rule says that this property of linear transformation holds for the derivative. And so this is equal to df, ADF. And so the derivative function, the derivative actually it's called an operator. The derivative operator is a linear transformation. Again, it's just a fancy name for function. We call it operator because it's a function on a particular vector space. And so we call it operator. Okay, so another example. Let T, why I call it T, I don't know. Maybe I should have called it I. Oh, let me just see. Oh, okay. Let T go from the set of continuous functions on the closed interval AB to the real numbers. Let this be defined as TF. Oh, that's where I should have said that. Let it be defined as, then it's, let it be defined, I forgot to put that in. Let it be defined as TF is the integral. T is a linear transformation. Here, wait, let me just put a little note here. So let df equal f prime. There. Just so I know to change my lecture notes. Okay, so then T is the linear transformation. Well, let's check T's linear transformation. T f plus g, I want to show that that's equal to tf plus tg. Well, tf plus g is just the integral from a to b of f plus g. Well, this is the integral from a to b of f of x plus g of by well, the linearity property of definite integrals. This is the same as the integral from a to b of f of x dx plus the integral from a to b of g of x dx. But this is just tf, and this is tg. And now let's check the second property holds, that t alpha f is alpha tf. Well, let's see. Well, let's see. T of alpha f is just the integral from a to b of alpha f. So this is the same as the integral from a to b. X is just alpha f of x. So this is integral from a to b of alpha f of x. I can bring constants outside of my integral. So this is alpha times the integral from a to b of f of x dx. But this integral from a to b of f of x dx is just tf. And so yes, indeed, this is a, oh, so all the calculus that you did, the main parts of it, the derivative and the integral, are linear transformations. So what that means is that all that stuff that you were doing in calculus is basically a subset of linear algebra. So what is linear algebra? Well, an example of it is calculus. So one little part of it is calculus. Now, we actually don't call it linear algebra we more or less call it functional analysis because it really more deals with infinite dimensional spaces than finite dimensional spaces. So fancier name because some of the techniques are a little different. You can use, you need to use different techniques for infinite dimensional vector spaces as compared to finite dimensional vector spaces. So usually we give it a different name when studying infinite dimensional vector spaces. Okay, next. Oh, and so this is, at the beginning, somewhat surprising because you think linear means something different. So let T be a transformation, a function, from the vector space C 0 R, the set of all continuous functions on R, to the C 0 R, the set of all continuous functions defined on the whole real line. So let's define this as TG at X is just X squared G of X. So we're multiplying by X squared. Is multiplication by X squared a linear? Linear? The answer is yes. And so one would, you're multiplying by X squared. So yes, that's going to be linear. Okay. So so then T is the linear transformation. So let's check. T at G plus H at X is, well, X squared, G plus H at X. Well, G plus H at X is G of X plus H of X. Let's multiply the X squared inside the parentheses. So it's X squared G of X plus X squared H of X. But this is TG at X, and this is TH at X. Is the same as, well, we define the sum of two functions as they're to be defined pointwise. I'm not sure what the question is, so I'm sorry. Can you explain how it turns into X squared? That's the definition. That's the definition of my function. So the definition of my function is, so, if I said f of x is equal to x squared, that's the definition of my function, right? I define my function as TG at x is x squared g of x. That's the definition. It's a definition of what the function is. Okay. Next, T of AG at X. So I want to show that this is equal to ATG. So let's see. Well, this is the same as, well, by definition, X squared AG times AG at X. But again, by the definition of scalar multiplication, this is just AG at X is just A times G of X. I can write this as A times X squared G of X, but X squared G of X is just TG at X. And so this is the same as ATG. And that's what you wanted to show. And so you've shown that this particular transformation is linear. Okay, so the null space. when you're talking about functions, we call this the kernel. When we're talking about vector spaces, we call this the null. When you're talking about systems of equations, you call them homogeneous solutions. Sometimes you call it the trivial solutions or the non-trivials. Actually, usually they call it the non-trivial solutions for your homogeneous system. So the null space of the operator of the linear transformation T is just a set of all V in your vector space such that TV is equal to 0. Okay. I see I've already gotten rid of all the little vectors because it's hard to think of them as vectors anymore. Even as vectors, meaning with an arrow. You know, what is the range of T? Well, the range of T is a set of all TV, such that V is in your vector space V. Oh, this is also, so hom lin VW. The set of all linear transformations from V to W. So sometimes it's called hom, H-O-M, V comma W, or len V comma W. It is the set of all linear transformations T from the vector space V into the vector space W. It turns out that this is actually a vector space. Oh, this is like one of the major theorems, which actually we will be going through in the book, but of course they'll be doing it at the beginning. They'll be doing it for linear equations. Let V be a finite dimensional vector space. Let T be a linear transformation from V into W. Then, so this notation just sort of is shorthand notation, so I don't have to keep writing out. Let T be a linear transformation from V to W. Then the range of T is a finite dimensional subspace, and the dimension of V is the dimension of the null space of T plus the dimension of the range of T. This turns out to be one of the fundamental theorems of linear algebra. The way Axler does it, he actually, he does it like almost immediately because it's really a fair if you make some easy definitions. Okay, so what is a matrix? So now this is more or less why why I'm going over this, because our book starts with matrices. But where the heck do matrices come up? And so, and where are they coming from in linear algebra? It's extremely mysterious. They just sort of pop out of thin air in the textbook that we're using. So let me give you the motivation for where they're coming from. So matrices. Let T be a linear transformation from V to W. Let V1 through Vn be a basis for V. Let W1 through Wm be a basis for W. and let A sub ij be the unique numbers such that tvj is equal to a1j w1 plus a2j w2 plus dot 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 a sub mj wm. Why are they unique? Because remember, for basis, it's a unique, every vector, this is some vector, it's going from a vector space to another vector space. So this is some vector. So for any vector here, I have a unique linear combination of elements from this basis. Gives you another vector. So a unique linear combination from this basis is found for any vector in W. So since this is a vector in W, I can write it as this unique linear combination of my basis. We will denote these by it is a matrix. So this is just the matrix associated with this and this linear transformation. So given, well, this basis for V, this basis for W, and this linear transformation between these two vector spaces, we have some numbers. We will call that array of numbers a matrix, and we'll denote it by MT. So that is how matrices arise. They arise because we have a unique representation of vectors because because we have a basis. So there's a unique representation of any vector in terms of these elements. And that array, that these numbers, we will form this array of numbers. So this way of sort of collecting this data and storing it in this little array, which we call a matrix, is because there is a basis to a vector space, and that any vector in your vector space is uniquely represented as a linear combination of your elements in your basis. So that then gives you the algebra of matrices. So from this, we will get an algebra of matrices. We will be forced to define if I want, so the set of linear transformations will be a vector space. If I want to define these matrices to also be a vector space, we are forced to define addition, scalar multiplication, and, well, matrix multiplication the way that they define in the book, just by using these sort of motivations. So, first off, if I want that, how do you, quote unquote, multiply functions? Well, you multiply functions by really doing composition. And so if I want that a composition of two linear transformations to correspond to matrix multiplication, we're forced to give that weird definition of matrix multiplication that they give in the other book. Okay, so let S be a linear transformation from the vector space V into the vector space W, and let T be a linear transformation from the vector space V into the vector space W. Notice that these are the same vector spaces, and let V be a vector in V. Then we will define as being a vector space from V into W by S plus V. S plus T at V is just S of V plus T of V. I mean, that's a very, very natural, how do you define addition? This is the same way you define addition for functions. And so this is a very natural way to define addition of transformations. Next, how do you define scalar multiplication? Well, the same way you define scalar multiplication for functions. So A times S at V is just A times S of V. And since W is a vector space, then so is VW. Okay, so let V1 through Vn be a basis for V, and let W1 through Wm be a basis for W. Then there exists unique set of numbers, A sub ij, such that, and this is there, are unique. So there exists is this little backwards E, and the little exclamation point says that it's a unique. So there are unique A sub ij such that S Vj is equal to A1 W1 plus A2j W2 plus dot 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 A sub mj Wm. There exists unique, where's my uniqueness? There exists some unique B sub ij such that T Vj is equal to B1j W1 plus B2j W2 plus dot 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 BMJ Wm. So if I want that matrix addition is just the matrix of linear transformation addition, then we must have the following. So we must have that S plus T Vj is equal to, well, it's a linear transformation. And so S Vj plus T Vj which is, I should have written it, well. I should have written it this way. S Vj plus T Vj is equal to S plus T Vj. Aha. Okay. Must equal A1j plus B1j W1 plus dot dot dot. And let me just see here, wait. VJs is not unique. No, that's just an element of your base basis. But actually, you can any other vector anywhere. The things that are unique is A and B. The A's and B's are unique. They're determined by your bases. So the A's and B's are determined by are uniquely determined by your bases. Okay. Oh, okay, good. Okay. Okay. Let me write. I don't like the way I wrote this at all. Okay, so I'm gonna erase this all. If only a S plus T Vj is equal to S Vj plus T Vj. Sorry about that, but I didn't like the way I wrote it. Equals. So SVJ these are the A's. A1J W1 plus A2J W2 plus dot 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 A sub M J WM. That's for the S's. For the T's, B1 J W1 plus dot 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 B sub M J WM is equal to. Well, I can regroup. I can say it's this plus this. So I can just say, well, it's W1J plus B1J W1 plus, regroup them all, plus A sub MJ plus BMJ WM. Ah. And so this says that to add these together, you just add their corresponding entries. A's and B's are scalar multiples. Yes, they are scalar multiples. They are scalar multiples because it's a scalar and that's a vector. So the W's are vectors and the A's and the B's are scalars. That is correct. In a linear combination, those numbers are scalars. And so those numbers here in this linear combination are scalars. They are members of your scalar, what's called your scalar field. That is correct. And so I have that to add these, okay, we have to do this. And so we are led to saying the way that you add two matrices is you just add their entries. And so in the book, we'll be doing a whole bunch of computations involving this notation. So if you're not quite comfortable with this notation yet, which you probably aren't, it doesn't matter. In about a week, you will see it so many times that you'll be very comfortable with it. We're going to be doing 50 pages of calculations in this. Yes, the entries are unique. Yes, that is correct. The entries in your matrix are unique depending on your linear transformation and your basis for your vector space. So there is only one matrix corresponding to a linear transformation and the bases for your vector spaces. That is correct. And so you said it correctly. And so the entries are unique numbers. Yes. Unique for one. So given a particular transformation, given bases for your two vector spaces, you have a unique represent the entries of your matrix. Okay. Also, so I almost got to. So that's matrix addition. Let's look at scalar multiplication. So also, suppose I want that the matrix multiplication here, the scalar multiplication of a matrix, I want it to be the same as the matrix of the scalar multiplication for a linear transformation. So suppose I want that the matrix of alpha S is just alpha times the matrix S. Well then, the only way to do this is as follows. We're led to these definitions for matrices. And so alpha S Vj is just alpha times SVJ. Well, SVJ is a JW1 plus A2JW2 plus dot 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 AMJWM. Let's multiply the alpha inside of the parentheses by A1JW1 plus alpha A2JW2 plus dot 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 alpha MJ alpha AMJWM. So we're led to the definition that alpha times the matrix A sub ij should be defined as the matrix with entries alpha A sub ij. Okay. Lastly, and this is the last part before I go on to, that's the last part of the intro, and then I probably look at the appendices for Coleman and Hill, and then start the actual text. Okay, so if S is a linear transformation from the vector space U into the vector space V, and T is a linear transformation from the vector space V into the vector space W, then I got to define it that way, yeah. Then we will define TS as a linear transformation from U to W by composition. And so it's just T composed with S. So let U1 through UM be basis for U, V1 through VN, oh, VP, let's do VP, sorry, be a basis for V, and let W1 through WN be a basis for W. Then there exists unique numbers A sub ij, such that S Uj is equal to A1 J1 V1 plus dot 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 A P J Vj plus. And there exists unique B sub ij such that T Vk is B1k W1 plus dot 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 BNK WN. So if I want the matrix T composed with S to be the matrix T times the matrix S, then I must have the following. So T composed with S at Uj is T of SUJ, but SUJ is this guy. So SUJ is just A1J V1 dot 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 APJVP. By the fact that T is linear transformation, well, remember any linear combination of, well, T of a linear combination of vectors is just the linear combination of T of those vectors. And so this is just A sub 1J T V1 plus A sub 2J VT T V2 plus dot 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 A sub PJ T VP. But what is TV1? Oh, there it is. Here's TV1. And so it's B11. Replace K here by 1. So B1, 1, U1, W1, B2, 1, W2, dot, 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 BN1, WN. Okay, but what's T of V2? Well, replace K by 2. What's dot, dot, dot? T, there it is. Well, we place K by P. Okay, so we get this. But now let's regroup things. So now let's look at this guy. So let me just look at this one here. So this is B11, so B11, B12, dot, 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 B1P, all times W1. And there J dot 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 A sub PJ. So I have that. Now let's look at this guy. Well, here are my W2s. Here are my B21 to B2P, B21 to B2P, and here are my A1J to APJ, A1J to APJ. Oh, okay, so those are those guys. Dot, 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 till the last one, till this guy. So the WNs, no, you're stupid. You're stupid. Okay. Okay. There. Wait. Here are the WNs. There they are. And here are the BN1s through BNP. There it is. Now it's correct. Sorry about that. And here are the the A1Js to the APJs. There it is. Okay. Typo. That's how you should define matrix multiplication. Let me redo the same thing. But now let's use summation notation. So in summation notation, it's very compact, but it doesn't have the sort of beauty of you seeing this sort of thing. But now that we've done this, you can see where each of these steps are. So T composed with S, Uj is T evaluate U of S of Uj. Now, what's S of Uj? So let's see, S, Uj. S, what the heck is S? Way up here. Here's SUJ. It's just the sum of I don't know, something, J, V, that same something. So say A, the sum over I of AIJ, VI going from 1 to P. And let's see what notation I used. What was the dummy index? I used K. So the sum K equaling 1 to P of AKJ, VK. Okay, well, So that was this first step here. Second step, you just put it inside. Well, oops. And so let's do the second step here. So by linearity of t, I'll just put this inside, and there it is. Now, what's tvk? Well, tvk, we're going to use an I there. So t, here it is. tvk is the sum, now I forgot, of I, of bik wi from I equaling 1 to n. And now let's just switch these around, which is this harder step, going from here to here. So switching these orders, or the order summation around. So switching the order summation around, oops, I get this last step here. But this is the ij member of my matrix then. It's the, so therefore, how do I define matrix multiplication? Well, if you have a matrix multiplied by a matrix with entries aij, it's a sum, k equaling 1 to p, of b sub ik, a sub kj. And that's what it is. So you're forced to give that definition. So this is the motivation for what we're going to be doing in chapter 1 for the first several sections of chapter 1. This is the motivation. We are forced to give these definitions. So there's no choice in the matter. I must give these definitions, and this is what I have to do. Okay, so that finishes off